Hey everyone, I want to do a video that goes over the sample term test 2, the multiple choice section, and just explain why each of them are true and false, since there's no justification in the solutions, and I feel like this will save you a lot of time in your studying. So, part 1, we have A is an M by N matrix, where R is the reduced row echelon form of A. And which of the following statements are going to be true? So we have the rank of A is less than the number of rows, then the reduced row echelon form should have at least one row of zeros. So if we have an M by N matrix here, and we are told that the rank is less than the number of rows, so let's just take a quick example. Let's do this. So let's say I have 3 rows, then the rank, I would need to have 2 leading entries, and I can't have any more. So in this case, try filling in the rest of the matrix. You'll realize that the only way that you can have the rank be less than the number of rows is if we do have 1 row of zeros, right? So A is true. And then B, we can use the same matrix for our justification here. If the rank of A is less than the number of columns, then the reduced row echelon form should have at least 1 column of zeros. And you can see here, we could fill this in with 1s and arbitrary constants here, and you'd see that the rank is 2, the number of columns is 4, and we don't have a column of zeros, so B must be false. 1C. For any x in Rn, the reduced row echelon form times x equals the 0 vector if and only if A times x equals the 0 vector. And this one we know is true. And that's because if we have a system where some matrix times x vector equals the 0 vector is consistent, and then we apply elementary row operations to it, that's not going to affect if the system is consistent or not. It's still the same system of equations, right? So it'll still have the same solution set. So we know that this is true because elementary row operations will not affect whether or not the system is consistent or not. 1D. The transpose of the reduced row echelon form of A is the reduced row echelon form of A transpose. And this one is just flat out not correct. If you were to go to like a reduced row echelon form calculator online or something like that, and like play different values and like take A and like reduce it and then take the transpose of that and then write that down and then transpose it from the beginning and then row reduce it, you'll see that they're not always going to be the same result. And that's just a property, like there's no property for this existing. This is just not correct. Question 2. Let x be some vector in R2 and consider the system of linear equations below. So, which of the following vector equations are solutions? Well, we'll find the solutions the same way that we always would, and that's by row reducing. Cool. And I'm not going to waste the time row reducing. It is pretty easy to row reduce, but just for the sake of time in this video. Well, these systems are the same system, or it's the same. One of them's the equation is just multiplied by 2. So we should get this. And we can tell from this, so if this is x1 and this is x2, then x2 should be a free variable, which means that we have x1, x2, well, this would be equal to 1 minus t, let's call x2 t. Then we could break this up further. We'd have 1, 0 plus t times the vector negative 1, 1. Great. And you can see immediately that 2a has got to be true because that's exactly what we solved for. Let's take a look at, because it's easy to dismiss this and be like, oh, I found the solution, that's it. But remember that this is like a line, a line that describes the solution set to the system of equations. And there can be like an equivalent equation of a line, just looks a little bit different, right? But for B, C, and D, it's just a matter of checking if the system is the same. So let's take a look at 2b. We see that the direction vector is just multiplied by -1. So this line is going in the same direction, just the other way. So that's good. But we need to check if 0, 1 is on the solution. So if we look at A, when t is equal to 1, then we can evaluate x to be equal to 0, 1, which is a point on the line. So that tells us that B is actually an equivalent system. So B is correct. 2C, we can immediately tell that the direction is not the same. -1, 1, and 1, 1, they are non-parallel vectors. So C is not correct. 2D, we're told, or we can say the exact same logic, 1, 0 is a completely different direction than -1 and 1. So D is also incorrect. Let's take a look at 3. So let A be an n by n matrix, and it's non-zero. So which of the following must be true? So is A invertible? And 3A, immediately we know that this is not true, because if we have a row of zeros, then this is not going to be an invertible matrix. The determinant of A would be equal to 0, so therefore it's not invertible. Okay. 3B, A is symmetric, and this is not true, and we can clearly see just by like a counter example right here, or it's just for clarity. This is not a symmetric matrix, right? And it's square. It is n by n. It's a 2 by 2 matrix. So it satisfies the conditions we have on A. It's non-zero and it's n by n, but it's not symmetric. So through a quick counterexample, we know that 3B is not correct. Okay. Let's take a look at 3C. If the rank of A is less than the number of, or I guess the number of rows or columns, then there's more than one way to express x, which is in the column space of A, as a linear combination of the columns of A. So let's break this down. I know that was a lot. So if the rank of A is less than n, then this is telling us that there's going to be a free variable, right? And that's a pretty big part here. So let's take this matrix as an example. Let's say A is equal to, and let's just choose it's got to be a square matrix, and the rank has to be less than 3. So we can let's do something like this. This is A, and it's saying that x is in the column space of A, which means that x is in the span of the columns, right? So we can express vector x as, x 1, 2, 3, right? And this is going to be equal to constant times the columns of A. And this question is asking us, is there one solution or is there going to be multiple solutions? So this is what we have, right? So let's think, how would we take a look at a system like this, right? Well, we could set up the matrix like this. Luckily it's already in reduced to echelon form. We got x1, x2, x3, right? This is how we'd solve this system. And we know that, so let me just be extra clear here. These columns here represent the constants for this system, right? Not to be confused by x1, x2, x3. This is just for some x, some arbitrary vector x. So C1 would be equal to or first we know that C3 would be a free variable. Let's call it t. C1 would be equal to x1 minus 2t, and C2 would be equal to x2 minus 3t. Great. So we can immediately tell here, since there's a free variable, there are multiple constants that we can so that we can express x as a linear combination of the columns of A. So this is true. There is more than one way. And what this comes down to is just the fact that we have a free variable. I just wanted to be super clear with all of this mumbo jumbo about x in the column space of A and like linear combinations of the columns, because it gets really confusing. But the key here is just knowing that the rank of A is less than n. There's going to be a free variable. There's more than one solution. 3D. If the rank of A is less than n, then the system of equations ax equals b is inconsistent for every non-zero b. And this one is not true. And we know that it's not true because what system rank theorem tells us is that if the rank of A is equal to the number of the rows that we have, then the system will be consistent for every b in R to the number of rows. But it's easy to say like, oh, that's not the case here. That means that we're inconsistent for every b, and that's not the case. It's just this question. We could have values or vectors b that still are solutions, but it just doesn't mean what system rank theorem is saying, that like there would be like any b would be a solution if the rank of A is equal to the number of rows. But just because this is not the case, it doesn't mean that we will have no solutions. It just means that we might not have all solutions, right? So 3D is false. Okay. Question 4. We have A is a 3x1 matrix and B is a 1x3 matrix, and they're both non-zero. Then the rank of A times B would be equal to either 0, 1, 2, or 3. So let's break this down. So if you're looking for a quick answer here, we know that the rank of AB must be equal to the rank of A. So this is what you can, like how you can get the answer. Like because A is a 3x1 matrix, we know that the rank of a 3x1 matrix will either be 0 or 1, but since it's a non-zero matrix, we know that it will be 1. So the answer is 1 here. But if you're not really comfortable with this definition right now, then keep watching and I'm going to attempt to explain it. So if we have, let's say, so we have A, which is, let's call it A, B, C, and we're multiplying it by B, which is a 1x3 matrix. Oh, I'm sorry, my A is the wrong way around here. So I've got A, B, C multiplied by, and this is a 1x3, let's call it D, E, F. So we know that the resultant 3x3 matrix would be equal to, and this is just matrix multiplication, just expressed a little bit differently in a way that you might not be used to seeing. That would be the first column. The second column would be E times ABC, and this last one would be F times ABC. Great. This is what we've got here, and you'll notice here, this here is AB, this is A, this is B, and you'll see here that the span of these columns here, that is those are all linear combinations, or in this case, they're scalar multiples of A. What that's telling us is that the column space of AB, or the span of the columns of AB, it's equal to the span of the columns of just A, right? Since AB, they're all just scalar multiples of A. And we know that rank and column space are very, very related, because the basis, or the dimension of the column space, or how many vectors we have in the basis for the column space, is equal to the rank. So that's how we can show that rank AB is equal to rank A. And then again, since A is a 3x1 matrix, it'll either be 0 or 1. We know it's a non-zero matrix, so the answer must be 1 here. Question 5. Let A be an M by N matrix where X is in Rn and B is in Rm. Everything's normal here. And so which of the following must be true? So 5a, if the system of equations ax equals b has an infinitely many solutions, then n must be equal to or greater than m. So we can clearly just think of an example where this is not true. So let's consider where m is greater than n. So let's say that we have this here. See, you can see that this is a 3x2 matrix. M is 3, n is 2, so m is greater than n. And you can see here we do have an infinite number of solutions, right? Because this value here, this x2, would be a free variable, indicating that we'd have multiple solutions here. So 5a is not correct. 5b, if the system of equations ax equals b has a unique solution, then n must be less than or equal to m. So for b, we know that this is true, and that's because if n was greater than m, that's like saying that we have more variables than we have number of equations, which means that anything where n is not equal to or less than m is going to have a parameter. So this has got to be true. 5c, if the system of equations ax equals b is inconsistent, then b is not in the column space of A, or b is not cannot be expressed as a linear combination of the columns of A. And this we know right away, this is true. Like by definition of ax equals b, if this was a consistent system, we'd say that b is in the column space of A. This is just by definition. So if ax equals b is not consistent, then b would not be in the column space of A. So 5d, if the system of equations ax equals b is consistent, then the rank of A must be equal to the number of rows. And this is not true. We know that the rank of A could be less than the number of rows, and we could still have a consistent system. So 5d is not correct. Question 6, we have let A be a square matrix. So which of the following must be true? So if AB equals BA for some B, which is also a 2x2 matrix, then A must be invertible. So this is not true. And it's because it's telling us that A and B are commutative, right? We can switch the order of the multiplication, and it doesn't matter. And then it says that then A must be invertible. And if like matrices being commutative doesn't have anything to do with one of them being invertible or not. So this one, we don't have enough information. So A is not true. 6b, if A commutes with an invertible matrix C, which is a 2x2 matrix, then A must commute with C inverse. So this is like saying AC is equal to CA. That's what it's telling us here. We know that AC equals CA. So we're trying to show that AC inverse equals C inverse A. So let's start by taking the left inverse of both sides. So let's do this. And we would get AC, oops, this would be C inverse AC equals, and C inverse times C is the identity matrix. So then we have this. And now let's take the right inverse of both sides. So we would get C inverse AC times C inverse equals A times C inverse. And then here on this right hand, on the left hand side, the C times C inverse, that is the identity matrix. So we would get C inverse times A is equal to A times C inverse. And we have just shown that A must commute with C inverse. This is also true. So B is correct. 6C, if A satisfies A squared equals I, then A is invertible. So if we have A squared equals I, we have A times A equals I, right? And we know that this is only true if and only if A is equal to A inverse. So clearly here, if A squared equals I is only true if A is equal to the inverse of itself, then A has to be invertible, or else it wouldn't be true. So 6C is correct. And finally we have 6D. If A squared equals A and A is not the zero matrix, then A is invertible. So if we had A times A equals A and A is not the zero matrix, is this invertible? Well, we know one solution here would be when A is equal to I, and in that case it's invertible. But there could be other solutions here where that is not the case. So for that reason, we can't really say that A is invertible here for every case. We know that I would work here for A equals I, but there are other solutions for A that we just don't know, and we can't say that all of those solutions are also going to be all of those other solutions are going to be invertible. So 6D is going to be false. And on that note, that is all of the multiple choice, and I'll catch you guys in the next video. See ya.